dive into the world of quantum physics as we introduce a key player, Richard Feynman. Born in the bustling city of New York in the early 20th century, Feynman was a prodigy from a young age, showing an uncanny talent for engineering. His curiosity led him to the Massachusetts Institute of Technology, where he began publishing papers in the Physical Review. From there, Feynman's career took off like a rocket. He was instrumental in the development of the atomic bomb during World War II, a testament to his genius, yet a burden he would carry throughout his life. After the war, Feynman's focus shifted to the mysteries of the quantum world. His work in quantum mechanics, quantum electrodynamics, and particle physics revolutionized our understanding of the universe. Feynman's most significant contribution to quantum physics is perhaps the Feynman diagrams, a tool that simplifies the representation of particle behavior. These diagrams, introduced in 1948, have transformed theoretical physics and are still widely used today. His brilliance was recognized globally when he was awarded the Nobel Prize in Physics in 1965, a testament to his groundbreaking contributions to quantum electrodynamics. But Feynman was more than just a brilliant scientist. He was a teacher, spending many years as a professor at the California Institute of Technology, where he had a knack for making complex theories understandable to his students and the public. A man of science with a knack for explaining complex quantum theories, Feynman laid the groundwork for our exploration of antimatter and anti-time. Feynman left us with more than just theories. He gave us a tool to visualize them: the Feynman diagrams. These diagrams, introduced by Richard Feynman in the late 40s, were nothing short of a revolution in theoretical physics. They are essentially pictorial representations of mathematical expressions, describing the behavior and interactions of subatomic particles. Now, if you're imagining something complex and convoluted, think again. The beauty of Feynman diagrams lies in their simplicity. They provide a simple visualization of complex particle interactions, making the abstract concepts of quantum field theory much more digestible. Feynman diagrams are used primarily in quantum field theory, a branch of physics that attempts to explain the fundamental forces of nature. But their applicability doesn't stop there. They can also be applied to other areas of physics, and even to statistical mechanics, a branch of physics that deals with the behavior of systems composed of a large number of particles. What's special about these diagrams is their role in calculating probability amplitudes in particle physics. Now, what's a probability amplitude? In the realm of quantum mechanics, it's a complex number that describes the behavior of systems. The square of the modulus of a probability amplitude represents a probability density. In simpler terms, it's a way to calculate the likelihood of a certain outcome in a quantum system. The diagrams represent perturbative contributions to the transition amplitude or correlation function of a quantum mechanical or statistical field theory. They're a graphical representation of the Wick's expansion of the perturbative S matrix, a mathematical object used in quantum field theory. But what's most remarkable about Feynman diagrams is that they are easier to work with than traditional methods and provide deep physical insight into particle interactions. By using Feynman diagrams, physicists can make accurate calculations that match experimental results, and that's a testament to their power and utility. The technique of renormalization compensates for infinite amplitudes in Feynman diagrams. This means that even when calculations seem to give infinite results, Feynman diagrams help physicists find finite, meaningful answers. Initially, Feynman diagrams were met with resistance from established physicists, but as their power and utility became evident, they've become widely accepted as a powerful tool in theoretical physics. There are currently no opposing opinions on the use of Feynman diagrams in quantum field theories. So Feynman diagrams, not just squiggly lines and arrows, but a revolutionary tool in understanding quantum physics. Now that we know Feynman and his diagrams, let's dive deeper into quantum mechanics with probability amplitudes. Imagine you're at a roulette table. You've placed your chips on red. The wheel spins, the ball is dropped, and as it dances around, your heart races. The outcome is uncertain, but the probability, the chance of it landing on red, is something you can calculate. This is a simple analogy for probability amplitudes in quantum mechanics. Although the quantum world is much more complex and intriguing, probability amplitudes are complex numbers that describe the behavior of particles in quantum systems. They're a bit like the roulette wheel, but instead of the ball landing on red or black, we have particles that could be in one state or another. The square of the modulus of a probability amplitude represents a probability density. That's a fancy way of saying it gives us the likelihood of finding a particle in a particular state. This concept is a key aspect of the Copenhagen interpretation of quantum mechanics, one of the many interpretations trying to make sense of the quantum world. In this interpretation, the wave function, which describes the state of a quantum system, is seen as a probability amplitude. The probability of an event happening, like a particle being found in a particular location, is given by the square of this wave function. However, in the quantum world, things are not as straightforward as the roulette wheel. The concept of quantum measurements and the behavior of systems were initially contested by renowned physicists like Schrödinger and Einstein. According to quantum mechanics, before you measure a particle's position, it doesn't have a definite place. It's in a superposition of states, spread out everywhere. It is only when we make a measurement that the particle appears in one place, with a probability determined by the square of the wave function. Another fascinating feature of quantum mechanics is that the act of measurement changes the system. If subsequent measurements are made on the same set of eigenstates, the values obtained will always be the same with a probability of 1. However, if the eigenstates of two observables are different, a measurement of one observable can change the probability amplitudes for subsequent measurements of the other observable. So what does all this mean? Well, probability amplitudes are a way for us to grapple with the inherent uncertainties of quantum mechanics. They don't give us exact answers, but they do provide the best guesses we can make based on the information we have. Just like the roulette wheel, we can't predict exactly where the ball will land, but we can calculate the odds. Probability amplitudes, a key to unlocking the uncertainties of quantum mechanics. From Feynman's diagrams and probability amplitudes, we now venture into the world of antimatter. Now, antimatter may sound like something out of a sci-fi movie, but it's very real and incredibly fascinating. Antimatter is, in essence, a mirror image of the matter we know and interact with daily. Every particle has an antiparticle, identical in every way, but with opposite charge. But what happens when matter and antimatter meet? Well, they annihilate each other, releasing energy in the process. But let's take a step back and explore an intriguing aspect of antimatter, its gravitational interaction. You see, gravity as we know it is a force of attraction. Every object in the universe, no matter how small, pulls on every other object. This is why apples fall from trees, and why we stay firmly planted on the ground instead of floating off into space. But what about antimatter? Does it behave the same way? Well, physicists have observed the gravitational interaction between matter and antimatter, and their findings are fascinating. They've discovered that gravity attracts both matter and antimatter at the same rate within experimental error. However, it's important to note that there's a 20% margin of error in this equivalence, leaving some room for further investigation. Early theories suggested gravitational repulsion between matter and antimatter. Imagine that, matter and antimatter repelling each other gravitationally. It would be as if apples flew away from the Earth instead of falling towards it. But these arguments were later overturned. The CPT theorem, a fundamental principle of quantum field theory, predicts that the gravitational mass of antimatter is the same as that of ordinary matter, ruling out the idea of repulsive gravity. However, as with any scientific topic, there have been various theories and arguments. Some theories propose the idea of repulsive gravity, such as a modified Dirac theory and classical theories of repulsive gravity based on general relativity. But these theories haven't been experimentally validated and have been met with criticism. One intriguing proposition comes from Marco and Caballé, who has proposed non-classical, non-quantum physical principles that could underlie a matter-antimatter gravitational repulsion. But again, this is a theoretical proposition and has yet to be confirmed by experimental evidence. Antimatter, not just the stuff of science fiction, but a key player in our understanding of the universe. As we continue to explore and understand the nature of antimatter and its gravitational interactions, we'll undoubtedly uncover more about the fundamental workings of the universe. In the grand finale, we tie everything together with the symmetrical time hypothesis. Now, imagine a dance floor. On one side, you have matter particles, grooving to the beat of time as we know it, moving forward. On the other side, you have antimatter particles, dancing to the same tune, but in the opposite direction. This is the crux of the symmetrical time hypothesis. It proposes that matter and antimatter are identical, save for their particles moving in opposite directions in time. It's like they're dancing the same dance, but one is doing it in rewind. So where does this idea come from? It's actually based on the work of our main man, Richard Feynman. Remember Feynman's interpretation of antimatter we discussed earlier? Feynman suggested that all properties of antimatter are consistent with the view that particles move backward in time. It's like watching a movie in reverse. The popcorn unpops, the credits roll at the beginning, and the hero unsaves the day. That's antimatter for you. But what does this mean for our understanding of the universe? Well, the symmetrical time hypothesis takes this concept a step further. It suggests that there are two universes expanding into the same space, but in opposite time directions. Yes, you heard it right. Two universes, like cosmic twins dancing to the beat of time, one moving forward and the other in reverse. This hypothesis helps us resolve some of the contradictions we face in physics, especially those between time symmetry and the irreversible flow of events. It's like having your cake and eating it too. But in this case, the cake is the universe, and eating it is understanding its fundamental laws. However, like all theories, the symmetrical time hypothesis isn't without its critics. There are those who question the idea of time symmetry, and others who argue about the implications of matter and antimatter moving in opposite time directions. But that's the beauty of science. It's a dance floor where ideas come to tango, waltz, and occasionally step on each other's toes. So there you have it, the symmetrical time hypothesis, a theory that could change our understanding of antimatter and time itself. It's a glimpse into a universe where time can dance in any direction it pleases, and antimatter and matter are just two sides of the same cosmic coin. It's a testament to the power of human curiosity and the relentless pursuit of understanding the mysteries of our universe. The symmetrical time hypothesis, a theory that could change our understanding of antimatter and time itself. From Feynman's groundbreaking theories to the intriguing world of antimatter, we've journeyed through the complexities of quantum physics. We started with the genius that was Richard Feynman, a man whose contributions to quantum electrodynamics changed the course of modern physics, and whose Feynman diagrams gave us valuable insight into the behavior of subatomic particles. We then delved into the concept of probability amplitudes, a key aspect of the Copenhagen interpretation of quantum mechanics. These complex numbers, as we learned, describe the behavior of systems, with the square of the modulus representing a probability density. This was a contested idea initially, but it now stands as a cornerstone of quantum mechanics. The story took a gravity-defying turn as we explored the gravitational interaction of antimatter. We learned that gravity attracts both matter and antimatter at the same rate, debunking early theoretical arguments against gravitational repulsion between the two. Then, we dove into the symmetrical time hypothesis, which proposes the existence of two universes expanding into the same space, but in opposite time directions. This idea, although it's still just a hypothesis, could potentially resolve the contradiction between time symmetry and the irreversible flow of events. These topics, while complex, are all interconnected. They represent the beauty of quantum physics and its capacity to challenge our understanding of the universe. Feynman's work, in particular, has been instrumental in propelling these theories forward, shaping the way we view and interpret the world of the subatomic. Yet, As enlightening as this journey has been, we must remember that we're still in the early stages of understanding these concepts. The world of quantum physics is vast and mysterious, filled with as many questions as there are answers. We've only scratched the surface of this fascinating field. So what are your thoughts on antimatter and anti-time? Share your ideas in the comments section below.